We tend to assume that chaos is the natural end state of the world, that a massive jumble of unpredictable events only results in more disorder. Yet, behind the millions of unrelated variables that define our daily lives, a specific mathematical shape is waiting to be found. Take the weather. Every time it rains, instruments track the precise duration and height of the accumulation. Meteorology is defined by the collision of thousands of unstable pressure systems. We see a similar spread in human biology. We use mechanical scales and sliding height rods to document traits like height and weight, physical data points dictated by a messy intersection of genetics and environment. We quantify cognitive performance in the same way, sitting students in standardized testing environments to record how thousands of different minds process information. Even in elite athletics, we track the time it takes for runners to cross a finish line, a number influenced by everything from wind speed to the individual psychology of the athlete. This animated diagram shows what happens when you plot all of those different measurements together. Despite coming from unrelated systems, the data points always form the same shape, a smooth, rounded hump that tapers precisely at the edges, a bell curve. This symmetry is the result of a mathematical truth that exists independently of the things we measure. It is a phenomenon known as the Central Limit Theorem. To scientists, this theorem is remarkable because it allows them to predict the behavior of a system without actually knowing how it works internally. Usually, a highly structured result requires a highly structured starting point, but here, the input doesn't matter. You can start with total, unorganized chaos and still arrive at a perfectly predictable outcome. Understanding this mechanism is vital because it provides the foundational lens through which we extract objective truth from a messy universe. The first people to exploit this order weren't academics, they were gamblers in 18th century London. This is Abraham de Moivre, a French mathematician and refugee who, unable to find a university post, made his living in the city's coffeehouses. De Moivre worked as a consultant for high-stakes gamblers, applying his mathematical talents to find a winning edge in games of chance that most people assumed were purely random. He realized that while predicting a single coin flip is impossible, combining many coin flips creates a reliable pattern. The more times you play the game, the more the results cluster around a specific center. By tracking these repetitions, de Moivre calculated the exact geometry of the normal distribution. He had found the first proof that even the most disorganized games of chance eventually settle into a predictable structure. To see how that structure emerges, we can run a simple test using the data from a single six-sided die. This is a flat, uniform bar chart showing the results of rolling a single die thousands of times. Because each number from 1 to 6 has an equal probability, the chart shows absolutely no structure. It's just a flat line. But if we change the experiment by rolling 10 dice at once and calculating the average of those 10 rolls, the pattern shifts. Instead of a flat line, the results begin to concentrate around the center point of 3.5. When we repeat that averaging process thousands of times, the flat distribution of the individual rolls vanishes completely. The data resolves into this smooth curve, with the probabilities falling away from the center in a precise mathematical ratio. In 1810, Pierre-Simon Laplace took this observation and turned it into a universal law. He proved that no matter how irregular the original data is, the average of enough samples will always produce this specific shape. The simple act of taking an average acts as an aggressive mathematical filter. It destroys the individual noise of random events and reveals the stable structure hidden underneath. This mathematical certainty has become the foundational pillar of modern empirical science, allowing researchers to draw reliable conclusions from limited sets of data. We can use this certainty to detect when a process isn't as random as expected. Suppose a gambler bets they can flip a coin 100 times, getting at least 45 heads. If you watch and they only manage to get 20, the math reveals if they're cheating. This is the normal distribution for coin flips. A result of only 20 heads sits on the extreme left edge of the tail, a zone covering just 0.15% of the curve. There is only a 1 in 600 chance a fair coin would produce that result. The math suggests the gambler is using a trick coin. This precise mechanism gives scientists confidence to separate genuine anomalies from expected random variance. For the theorem to hold, the samples being measured must be independent. A person's height has nothing to do with their breakfast, keeping those effects entirely separate. If the variables are linked or biased, the curve will not form correctly. There are also limits when dealing with extreme events. While the theorem explains the average, it cannot easily predict outliers like 100-year floods, which require entirely different statistical models. Yet, despite these boundaries, the theorem remains our most vital tool for interpreting the natural world. It lets us combine thousands of independent measurements to find a clear path through the noise. It shows us that beneath the apparent disorder of the universe, a beautiful and inescapable mathematical architecture remains constant. When enough random events collide, the chaos